Hello everyone. Thank you very much for watching my presentation video. I'm Koki Nagahama, one of the research student member of Shibata Institute of Technology. Now, I'll introduce my research titled Resource Utilization Prediction Model for SLAM Offload Edge. In recent years, the use of autonomous mobile robots has been proposed in Japan as the world's most robotic society. This aims to popularize intelligent robots that support daily life, and it has been proposed that multiple intelligent autonomous mobile robots will be moved in cooperation in the city or at home in the future. Along with this, advanced calculation processing, such as deep learning and SLAM, is required. So an edge that can be placed near the users and processed was proposed. Edge is a distributed server with the wireless function of the next generation communication standard 5G that can be placed near users and sensor nodes in response to advanced calculation processing requests such as IoT devices. It is expected to be able to solve problems such as latency, network bandwidth, and high energy consumption, which have been drawbacks in conventional cloud computing. Currently, edge computing, which uses edge, is attracting attention. Previous studies have shown the effectiveness of memory reduction by optimization methods that applies the principle of divide and conquer proposed by Benjamin et al. And Monte Carlo localization method proposed by Alexander et al. However, since they only consider specific SLAM algorithms, they can only achieve specific application improvements, which poses a problem with versatility. As a related research, in the research conducted by Okawa et al., while offloading the SLAM calculation processing of virtual SLAM, even low power consumption computers such as Raspberry Pi can give the robot body the processing power equivalent to a PC by linking with the cloud. It was shown that it is possible to perform SLAM processing with performance equal to or better than that of the case. However, in the paper, only the CPU is being considered for SLAM load configuration. In the research conducted by Fukutomi et al., a method of constructing a resource management mechanism using a master-slave mechanism was proposed, which has a high affinity with the publish-subscribe model in the loss distributed platform, and using it to perform processing offload for another slave is used. It assumes that the usage rate of each CPU, memory, and disk is different for each host machine, and the formula related to the resource margin is defined. As a result, it has been shown that processing of stateful loss nodes can be taken over across host machines, and the scalability is ensured in a loss distributed environment by actual application evaluation using SLAM. However, since processing is performed using communication between loss and master slave, there are restrictions only on the overhead due to communication and the resources of the host machine, and offload processing is completed within the slave node group. In the environment of multiple robots with limited resources, it is not assumed that the memory consumption exceeds the limits of the entire slave node group. Therefore, in this research, we aim to solve these problems and confirm versatile by offloading edge with sufficient computer resources. We conducted a preliminary experiment with the aim of investigating the load composition of SLAM, I measured the CPU and the memory usage rate when running the SLAM applications in a 6-meter square room with my own measurement tool. The experimental environment is as shown in the figure below. The mapping algorithms use dmapping, which is a two-dimensional occupied grid mapping method. I will describe about ROS, Robot Operating System. ROS is middleware for robots, and its main functions are device drivers, libraries, visualization tools, and message communication. On the ROS network, communication between nodes is performed by publish-subscribe communication that transfer messages from the publish side node to the subscribe side node. The figure below is a model that simply shows the mechanism of data exchange in publish-subscribe communication. This is the actual photo taken from the preliminary experiment. After connecting to the robot using SSH, start the measurement program first, and then start up ROS node in another terminal. We performed teleoperation by key operation from a remote PC and made a round of the room. The self-made program for measurement is designed to acquire the CPU and the memory usage rate at 1 second intervals and outputs them as CSV. You can see the map generated based on the distance measurement is displayed on the right side of the monitor. This is a result of a preliminary experiment. First, regarding the CPU, you can see that it uses a lot of CPU when starting the ROS node. On the other hand, regarding memory, it was found that memory started to rise at the same timing as the ROS node was started, and the high load was maintained until the ROS node was stopped. In this state, if a ROS node or process that can only be executed on the robot is executed, the process may hang. So it is important to reduce the memory load in SLAM. The purpose of this research is to propose and realize the optimal memory offload method for the edge during SLAM processing. This is our proposal. In order to achieve memory offload for the edge, it is necessary to avoid the offload process itself to become a load. Therefore, in this research, we propose a predictive model for deciding whether to offload from the memory component and the load state of the network. It is necessary to create a predictive model and make a guess in order to judge whether it can be offloaded. Therefore, we considered a multiple regression model using memory components and created the following memory usage prediction formula. A1 to A4 are particle regression coefficients, and mstack, mheap, mbuff, and mcache are the amount of data in the stack, heap, buffer, and cache memory, respectively. Also, multiple regression model is important for making predictions because it has the advantage of keeping the error small. We also created a predictive formula for network load conditions. Nload is network level, and B1 and B2 is coefficient. Nsend and nreceive is the data size of network communication transmission or reception. And nsend bar or nreceive bar is the average data size of network communication transmission and reception. N-load was defined as an indicator of how much network load is being applied. It is necessary to make a load prediction that considers how much transmission and reception affect the network, not an index of how much bandwidth is being used. This N-load has a great influence on the decision of the execution timing of the offload processing. In addition, the coefficients B1 and B2 are defined by the following two equations. The mean function returns the smallest value contained in the argument. The product of the amount of using data using the band, the amount of data transmitted in B1, and the amount of data received in B2 divided by the average mean of each is the reciprocal of the product. We evaluated the proposed prediction model. In addition to the self-made tools mentioned above, I used VMstat, which can acquire the amount of data in the buffer and cache, and Valgrind, which can acquire the amount of data in the stack and heap memory. As for the self-made tool, the function that can acquire the network communication amount is added to the one that can acquire the CPU or memory usage rate mentioned above. When SLAM was executed, the data set was created by adding three types of memory load of 0%, 25%, and 50%. I'll explain the flow of evaluation. First, if we need to do additional load, use the stress command to load it. Start our own measurement tool and VMstat, run the loss node on Valgrind. Finally, we did evaluation and analysis. As you can see in the output example of Valgrind in the lower right, it fits in a form that is not suitable for the input data or multiple regression analysis. So the data was formatted using Excel. Regarding the collected data, we used 180 seconds of continuous data, of which 80% was used for training data for model construction, and the remaining 20% was used for model evaluation. The evaluation result of the memory consumption prediction model is shown. It was confirmed that the forecast was close to the actual value from the graph. The maximum error rate is an index that means what was the ratio of the error that occurred between the actual value and the predicted value. It is defined as the absolute value of the error divided by the actual value. The maximum error rate is less than 2% for all the datasets used, indicating that the memory usage prediction is highly accurate. On the other hand, looking at the coefficient of determination associated with multiple regression analysis, the accuracy of the prediction model is quite high, with the coefficient of determination approaching 0.80 for dataset 1 and 2 with relatively low loads. However, it cannot be said that the accuracy is high because the coefficient of determination is as small as 0.50 in the heavily loaded dataset 3. For this reason, improving prediction accuracy is an issue. Next, we evaluated the network load prediction model. As with the evaluation of the network load prediction model, the evaluation is performed using the acquired data. As quantitative factors used in this evaluation, the upper and lower limits of N loads, the probability that the timing when the network transmission loads can be judged to appear will appear, and how long the timing when the network transmission loads can be judged to continue has continued adapted meaning maximum duration time. This is evaluation result of network load prediction model. First, focusing on the upper and lower limits of N load, the upper limit is in the positive range and the lower limit is in the negative range in any dataset. It has become possible to quantitatively understand how much the amount of transmission or reception affects the network load from the previous statistics. Next, looking at the probability that the timing when it can be judged that the load of network transmission is small appears, we found that there is a timing when it can be judged the influence of network transmission is small with a probability of 5% or more in each dataset. It has been suggested that the offload process may be executed once every 3.3 seconds, even under heavy load. Furthermore, the value of the maximum duration in without said network transmission may be available for offload processing for at least 1 second in a row, even if the memory load is high and the processing may stop. When using the next generation communication standard, 5G, which is being introduced recently for networks connected to the edge, it can be estimated that the amount of data sent per second is sufficiently small in terms of bandwidth. From these things, it seems that sufficient performance can be secured for offloading. Conclusion. The method we propose suggests that the method of modeling the memory and the network with the system resources is sufficiently effective in predicting and determining the timing of memory consumption associated with memory offload. However, since the accuracy varies when the memory load from other processes is high, improving the prediction accuracy can be considered as an issue. As future work, we plan to design and implement a system that can realize optimal memory load processing by combining ROS, KVS, key value store, Kubernetes, and so on with the prediction model. This is the end of slides. Thank you for listening. If you have any questions, please send me messages.